Today I will present a 2D hierarchical dielectric analysis of finite electrode array using FreeFEM++. So my name is Pascal Ventura. I have been working on this project with Frédéric Hecht and Pierre Dufillier from Microsemi, Hartford, USA. So this is the outline of my talks. After an introduction, I will present the principles of surface acoustic wave interdigitated transducer component. Then I will show the physical models and following the rational formulation for the whole array of electrodes, and go to the idea of hierarchical numerical model to analyze the array of electrodes. Give some information about FreeFEM++ code, especially the input file, and show the first validation of the code using previous Green's function code. And finally,
Pascal, we are not seeing your entire paper.
Excuse me?
We are not seeing your entire presentation.
I see me.
Okay.
The screen? You don't see my...
We see a half of it.
Ah, okay.
Only a problem for you, George.
Okay.
Okay.
I see all of it as well.
Okay. So I follow. So the introduction. In the past, various numerical models have been published to compute the harmonic admittance of a periodic surface acoustic wave transducer. We can mention Ballandra's work in 2002, my work in 2001, and Ken Hashimoto work in 2011. In 2013, with Frédéric Hecht, we have been published an original numerical model that uses efficient variational formulation to deal with periodicity and of the geometrical boundary condition. This work uses a boundary integral formulation for the semi-infinite space. It is written in FreeFEM++. This work lead to derivation of p-matrix parameter needed by surface acoustic wave designer to analyze finite transducer, and we obtained a very good comparison with experimental values for slow resonators. Recently, in 2018, Julius Koskela published a new technique that is very efficient to simulate a finite surface acoustic wave transducer based on a small number of elementary cells. These new techniques consist in subtracting each element cell using a tree concatenation to analyze the whole transducer. So perfectly matched layer this time is employed to account for semi-infinite piezoelectric and dielectric media. The work I will present today is a first step. We succeeded in writing a 2D finite transducer FreeFEM++ script that consider only dielectric effects and static PML. We refer to Bardi work in 1898 has been used. We will show validation. So the principle of surface acoustic wave transducer. So you have first, it consists on a piezoelectric substrate covered with interdigitated transducer. So it works like this. The surface acoustic wave is launched by the left transducer, is propagating and is detected by the second transducer. You can see typical finger width versus operating frequency, ranging from 100 megahertz to 2 gigahertz. If we consider transducer used, they are often based on a few basic cells which are concatenated. So this is this remark that lead us to present work, current work. We use simplified assumptions, so isotropic dielectric media are assumed above and below the electrode. For this model, we use only a dielectric medium. 2D analysis assumed because it is a very long electrode. We neglect losses in the electrodes, and the thickness also of electrodes are neglected. The physical model presents the physical model. So for the physical fields, you have the potential, electrical potential, E the electrical field, D the electrical displacement field. You have the epsilon, the isotropic dielectric tensor. Both dielectric media obeys the Maxwell's quasi-static equation, divergence D equals 0. The constitutive equations are this one, the relationship between the electrical displacement and the electric field via epsilon. Let us present first the variational formulation for the whole array of electrodes. So you have a few number of electrodes is typically a few hundreds, and they are either connected to one electrical port or to the other. You can also have 3 electrical ports or more. So in the present study, we only consider the electric domain. So you have 2 dielectric domains, one up that will be the vacuum, for example, of the air, and the below you have another dielectric domain that can be dielectric media. So variational formulation is quite simple. At the boundary, you have no free condition. So it is like this. So you have the integral of E psi scalar epsilon E phi equals 0 integral, and you have only to consider Dirichlet boundary condition for each electrode. So this is the applied voltage. Let us go now to the hierarchical numerical model. So the purpose is to analyze only the elementary electrode. So we write the variational formulation for each elementary electrode that contains only one electrode. It is a definition. And we compute the FEM finite element stiffness matrix for this cell. The second step, we are going to remove the internal degrees of freedom and keep in only the potential degrees of freedom of the lateral boundary, left and right, and of the potential of the electrode that is assumed equipotential. The step 3 is now to build the entire the whole transducer array of electrode by concatenated with concatenation of the elementary cells and more. The fourth step is now to apply the Dirichlet boundary condition at the end of the algorithm and compute the field in the whole electrode array, in the whole domain. Finally, we will compute the charge distribution at the boundary of electrode. So this is an elementary cell bounded by 4 boundaries, so the up and down, the left and right. You have a dielectric domain two dielectric domain, and you have a static PML part that will to account for semi-infinite space. I don't have time to give details about static PMLs, but it is like it simulates the fact that you have semi-infinite space. So the first step is to write the variational formulation for this elementary cell. So you have the domain integral on omega, and you have a border integral with the dielectric displacement at the left and right boundary, plus the Dirichlet boundary condition for the potential of the electrode. So we can show that it is we only compute the FEM matrix K for the bilinear form, and it's no need to consider the second member because with the concatenation it will be removed. So we just consider the stiffness matrix. So the second step is to sort on one part the internal degrees of freedom, and in their part left and right boundaries and the electrode potential degrees of freedom. This is the E and XE, and we keep only 1 degree of freedom for the electrode potential. So you have the K matrix with permutation is sorted like that. And in order to remove the internal degrees of freedom, we compute the Schur complement like this. So first the B matrix used to get internal degrees of freedom, knowing the UE degrees of freedom, and the Schur complement matrix is S. In the following step, now it's the concatenation of cells, or you can concatenate elementary cell and after more cell that contains more electrodes, but the way of doing is the same. You have S matrix for the left and S matrix for the right electrode. And first we derive the SL union R left union right matrix by putting together the common all the degrees of freedom of both matrix, and considering the fact that the middle interface between the left and right electrodes is common, the same degrees of freedom, and we are also to consider the connection between electrical ports of the left and right electrodes. It is an algebraic operation. Now we operate another Schur complement as previously to remove the middle boundary degrees of freedom, and we obtain a new SC Schur complement matrix, and the BE matrix are obtained for the concatenated cells. And we have also to build a M matrix that allow to compute internal degrees of freedom of the left and right cells, knowing the remaining degrees of freedom. It's to be able to go back to all the degrees of freedom of both cells. The step 4 is at the end of all the concatenation processes, you will have only the electrical port degrees of freedom remaining. And now it is a time to apply Dirichlet boundary condition on the electrical port 1 to N regarding the applied voltage. So now you can compute the potential degrees of freedom for the whole electrode array. Once you have the potential in the domain, the charge distribution at the boundary of electrodes is the jump of the normal derivative, the normal projection of the electrical displacement when crossing the boundary. So it is done by choosing 2 points very close to the point where we want to compute the electrical charge, and making this operation, subtracting both terms up and down. Now let us, so we write all the FreeFEM++ code, and I want to focus on the input file. So we define 3 kind of elementary cells, 2 types: the left boundary type, the right boundary type, and the intermediate cells. So we put some margin to make a distance between the PML and the domain, like this. So we have some geometrical data. And this is an example for a transducer. One is so you have the concatenation of identical cells. Here it's a potential 1 or 0. So I have 2, 1, 0, and 2, 1. So here, this is a description of the input file. You have a description of the cell geometry, the elementary cell geometry. Here you have only the need to 3 elementary cells, the left. So the bracket 1, the intermediate cells, and the left and the right boundary. So 3 cells. It is described here with all the geometrical. And now you have to describe all the concatenations. For example, I wrote the first concatenation. So 2 is you concatenate 2 with 1, or 2 is the both cells. Excuse me. So you concatenate the left to the intermediate cells, right, and you get this is a description of the concatenation, the port. You have 1 port. The first line is the first port of the concatenated cells, and it has the 0 potential of the first cells and 0 potential of the right cells. So it is a little we have to be careful about, but it is done. It is no problem. So this is the validation of the code. So we compare for this transducer the electrical charges with the Green's function code, and it gives quite good comparison, and the accuracy is very good regarding the devices needed. So as a conclusion, I can say like a new hierarchical numerical model has been developed successfully in the FreeFEM++ environment to simulate a 2D finite array of electrodes with only, in that case, dielectric media. The electrical charge distribution has been compared with previous Green's function computation and gives excellent fits. For the future is to generalize the hierarchical numerical code to deal first with acoustics, surface acoustics transducer. We can and follow to the 3D challenge simulation, because there are much more degrees of freedom, and it ended with full matrices. And I can say that this work is quite general. It can be applied to like it has been applied to dielectric, but it can be applied to mechanics and lot of fields where you have the entire structure built with a few basic elements. So thank you.
Oh, merci, Pascal. There are some questions, remark, comment. Okay, Pascal, I've just some remark. The way to do the same with general things, with piezoelectric stuff, I think it is not really difficult because the structure of the code does not change. For the 3D problem, it's another story because now the left part and the right part, which are the place where you have the degree of freedom, and you have full matrices depending of this side. So if you want to play with full matrices, more than I say 6,000 degrees of freedom will be a real limit. So you have to divide by 2. So you must have less than 3,000 degrees of freedom on each left part and right part.
Okay.
That's.
Thank you, Frederick.
Okay. So don't forget to send me the slide.
Okay,
I will put the slide on the website. And this is true for every speaker. This.